Mhm.
All right, everybody. Good morning and welcome to day 3 of the Animas and San Juan Watersheds Week. I imagine most of you have already tuned into some of our previous webinars, so I'll keep our participation guidelines abbreviated so we can get to our wonderful presenters today. If you notice that you're having any connectivity issues viewing the webinar, you can either try to relocate to another location that might have better internet connection, although please do remember to continue to follow your state's guidelines regarding social distancing. Or some other common things that you can do is to use a wired Ethernet connection, close any programs or apps that might be running in the background, reduce the video quality by unchecking the Enable HD feature, mute your audio, although many of you are already muted, and ensure that you're using a network that isn't being used by a lot of other people. You'll notice that you have your Zoom attendee screen here. So the common ways that you'll interact with our presenters today is you have the Q&A box where you can submit questions. We'll also be allowing attendees to use the hand raise function to ask questions orally to our presenters. And lastly, if neither of those work, we also have a chat box that's open so that if you're having any other issues or any other comments that you'd like to make to our presenters, that's available to you as well. With that, I'd like to turn things over today to our MC for this day's session, Johanna Blake. Johanna is a hydrologist and geochemist with the U.S. Geological Survey, New Mexico Water Science Center. She earned her master's and PhD in Earth and Environmental Sciences from Lehigh University in Bethlehem, Pennsylvania. Her undergraduate degree in Earth and Planetary Sciences is from the University of New Mexico. Johanna is well-versed in analytic inorganic chemistry, natural and anthropogenic metals, and mining-related mobility of elements such as arsenic, uranium, lead, and chromium. She combines her love of geology, geomorphology, and geochemistry to understand complex environmental systems. So Johanna, I'll let you take it from here.
Okay, thanks, Mark. And thanks everybody for joining us yet again for this Animas and San Juan Watersheds Week. I think it's been a great conference so far. And just to kind of recap what was talked about yesterday, a number of people discussed approaches to multi-jurisdictional watershed issues, and I think that was really interesting, especially given the broad range of different people involved in the work along the Animas and San Juan. Today is going to be a focus on chemistry, which, as Mark mentioned, I'm a geochemist, and so this is something I'm very passionate about. And we're going to have a number of talks about different aspects of chemistry, both in water and in sediments and associated with agriculture. We have, let's see, four talks and one poster presentation, and then we are going to have another giveaway prize drawing. Today we have 2 WRRI coffee mugs, 1 copy of 100 Years of Water Wars in New Mexico, a hydrological cycle poster set provided by USGS and myself. And then 1 blue fluorite mineral provided by the New Mexico Bureau of Geology Mineral Museum. And so without further ado, I'm going to introduce our first speaker, Chris Barrios. Chris is going to be talking about work that he and others from the New Mexico Environment Department have done on lead concentrations in the Animas River in New Mexico. Chris is currently the manager of the Monitoring, Assessment and Standards section in the New Mexico Environment Department, Surface Water Quality Bureau. He has a BS in geology from Florida State University and is a licensed professional geologist. Prior to his current role at NMED, he was the monitoring team lead in the Monitoring, Assessment and Standards section from 2015 through 2016. Chris began his career in Florida in 2000 at the Florida Department of Environmental Protection and has at various times worked on underground storage tank remediation projects, aquifer mapping, hydrogeochemical analysis, surface water and groundwater monitoring, and SCADA design and operation. So with that, I will turn it over to Chris.
Good morning. Thanks for having me. Let me see if I can get the share screen to work here. Yes, I do want to stop other screen sharing. And here we go. How's that look?
Looks good, Chris.
Okay, great. Well, thank you. As Joanna said, I'm Chris Barrios. I'm with the Monitoring, Assessment, and Standards section with the Surface Water Quality Bureau. And we're going to talk today about recent assessments that we've completed into lead concentrations in the Animas River in New Mexico. Okay, at the Surface Water Quality Bureau, our mission is to preserve, protect, and improve New Mexico's surface water quality for present and future generations. And in the Monitoring, Assessment, and Standards section, we meet this goal through 1, setting standards, designated uses and criteria, then monitoring and assessing against those standards, and then finally reporting the results of our findings. And the main vehicle of our report is called the integrated report. Every even-numbered year, we submit this report to the public and EPA that describes water quality and a list of all the water bodies that are not attaining standards. This is also known as the 303D, 305B integrated report, or in shorthand, as we like to call it, the IR. So it is required in federal rule that states must use all existing and readily available water quality related data and information in their assessments. And also these data must meet quality control and quality assurance requirements. And also, we want to use data that are both current and relevant. So we set a threshold of the most recent 5 years for our data assessments. So the key data sets that we used in our most recent assessments include our routine rotating watershed surveys. The most recent that we've completed and validated was from 2017, 2018. We also used our 2015-2016 post-Gold King mine spill monitoring data and data available from USGS and EPA Region 8. And on the right is a map of our rotating watersheds. And you can see in 2017-2018, the red colored watersheds include the San Juan. So the Animas River in New Mexico is split into two units. We call them assessment units. And these are physiographic regions of the watershed that represent more or less a consistent character of water quality and watershed influence. On the left-hand side, the blue colored portion of the Animas River, that is from the San Juan River to Estes Arroyo in Aztec. And in our assessment, that included 8 monitoring locations, 2 from us, 2 USGS, and 4 from EPA Region 8. And then on the right-hand side, that is the Animas River from Estes Arroyo to the Southern Ute, Colorado boundary. Both assessment units are approximately equal, 27 kilometers versus 30 kilometers, and have a fair number of monitoring stations in each. So our dissolved lead criteria that we use to assess these waters are in the table on this page. We have 4 different designated uses with dissolved lead criteria, including irrigation, has a criterion of 5,000 micrograms per liter, livestock watering at 100 micrograms per liter, domestic water supply at 15 micrograms per liter, and aquatic life use, which is a little different. It's a hardness-based equation. So the criteria actually increases as hardness goes up. And you can see in the chart on the bottom, I've plotted the 2 lower designated use criteria, domestic water supply at 15 and aquatic life use. You see the increasing line there as hardness increases. And I'll just point out also that at 400, at a hardness of 400, the equation maxes out. And from that hardness forward, we just use a value of 400. And that's about roughly 11 micrograms per liter. So when taking the available data for the past 5 years, we take our concentration and hardness, and that is plotted now against the chart that I showed you previously. Any values that are above the black line for aquatic life use are exceedances. And in our comprehensive assessment and listing methodology, a water body is impaired for toxic parameters if 2 or more exceedances are documented in a 3-year period. So I have split the 2 AUs into different symbology. The lower AU is represented by the squares, and the upper upstream assessment unit is represented by the circles. You can see there are 2 circles above the line, which means we did have 2 exceedances of dissolved lead in the assessment unit from Estes Arroyo to the Southern Ute boundary. So as a recent development, that's the first lead impairment that we have for the Animas River. I wanted to look into the historical record to see if this is a new development. Is this an outlier, or is this a pattern that we've seen in the past? So looking at the available data from EPA's water quality portal, also known as STORAD to some folks, I pulled out the data from 2000 to 2019. I did look at the historical data before that, which does go back into the 1930s. However, there seemed to be detection limit issues and some QA/QC problems, and I really didn't feel confident using anything prior to fall of 2000. So this inventory includes both data that we've collected, more recent data from EPA Region 8, USGS, and also the National Park Service did some data collection in 2005. So plotting that data out using the dissolved lead exceedance ratio, which is simply, the exceedance ratio is the comparison of the criteria at that instantaneous hardness. So it helps you look at values that would otherwise be the same with different hardnesses that could result in one case having an impairment versus not. So any value over 1 is an impairment in this, is an impaired result in this chart. So a couple things stand out. One is that the data set from 2000 through what's available in 2010, they look pretty consistent. And then following the Gold King mine spill, there's an interesting pattern of increases during spring runoff. So there are a couple of tests that we can do to see if these apparent changes are real or just look interesting visually. So the first is just to plot the pre-Gold King and post-Gold King results against each other and do a t-test for independent means. The result of that test using the 46 pre-Gold King samples and the 111 post-Gold King samples does show a significant statistical difference in the two populations. So another observation is that the concentrations and exceedance ratios seem to be more correlated to discharge. So using discharge data from the USGS gauge at Cedar Hill, these two charts show the correlation between sample results and discharge from pre-Gold King on the left and post-Gold King on the right. And the little blue box in the chart on the right is just the range of pre-Gold King mine data, the chart on the left to give you some contextual information. So there is a marked improvement in the correlation between discharge and dissolved lead concentration and exceedance ratio. And if not for a single event that seems to be an outlier at the bottom here, the correlation would be a little bit stronger. So another test we can run to determine the significance of the change is to look at the loading, which is the concentration times the discharge, and see if we can determine through change point analysis if there were any significant changes in the data set over that time. So the change point analysis uses a cumulative average departure, which is taking the entire data set and looking at the average. Each value then is ranked in order and then gets a departure from that average. You add those up cumulatively and you look for breaks in slope. And those are identified in this chart by the red vertical lines. Then those breaks in slope are validated by doing a bootstrap analysis where you take the same data set, reorder it, and see if you can create these maximum cumulative departures randomly. And if you can't, that means that you have a structured order and that the change was significant. And that's what these two small charts are on the right, just two screenshots from that analysis. So in the main chart, the first vertical line on the left indicates a change during the spring of 2016. And the second vertical line towards the right represents a change in the spring of 2019. And the box plots represent the population statistics for each of those periods. And comparing those populations does result in significant differences between those populations. So yet another way to verify that a significant change did happen. So knowing that, we wanted to look into the watershed further up to see if we could tell where these lead results could be influenced, where they could be coming from, and seeing those patterns in increases in spring runoff. I plotted out in these panels on the left, going from Farmington all the way up to Silverton, lead results, dissolved lead results from the springs of 2016, 2017, 18, and 19. And these vertical bars on the panels show the relative lead results from a single station. So what's interesting to see and was reflected in the time series chart earlier is that if you look at the Animas River from Farmington in New Mexico, from Farmington to the state line, you do see increases in dissolved lead during that time. But another pattern develops, which is also of note, which is that the relative concentration each spring changes and shifts downstream. So in spring 2016, you can see the highest concentrations are just upstream and downstream of Durango. In 2017, that flattens out some. 2018 was kind of odd because it was such a dry year and there wasn't much spring runoff. Concentrations were pretty low. But in 2019, the relative concentration has shifted downstream into New Mexico. And then contrast that with the spring of 2010, which is the last year of data available before Gold King Mine. Concentrations are very flat, and those bars all represent the detection limit. The chart on the upper right is another way of graphically representing this. Like New Mexico, Colorado also splits its stream segments into an assessment unit. And these color bars represent the assessment units from the headwaters north of or upstream of Silverton all the way down to Farmington. Beginning with the light colored, which are the most downstream, and the darker colored, which are the most upstream. And you can see that same pattern through the spring runoff in successive years post Gold King, with the 2019 results showing a shift in concentration downstream. So up to this point, I've focused mostly on dissolved lead since that's the fraction included in our surface water criteria. However, total lead is also a concern. The EPA action level for drinking water is 15 micrograms per liter. And in 2016, a study by NMED found a correlation between turbidity and total lead, which led to the city of Farmington installing a SCADA system to shut off intake from the Animas River during high turbidity, high flow events. And that correlation between turbidity and total lead is shown on the left. And like dissolved lead, total lead also does show that same pattern through the spring runoff of 2016 through 2019, a shift in relative concentration downstream. So the obvious change point between 2015, 2016, and the first change in our change point analysis is the 2015 Gold King mine spill. In the analysis of the transport and fate of metals released from the Gold King mine, published by EPA in January 2017, they estimated that 490,000 kilograms of metals, mostly iron and aluminum, were released into the Animas River over the 9-hour period following the release. And approximately 90% of that solid metal load settled in the Animas River. And they also noted at the time for metals from the release may have contributed to exceedances during the 2016 spring snowmelt. The report also goes on to say that by the fall of 2016, contamination of metals from the Gold King release had been transported through the system to Lake Powell. Based on our recent data and analysis, we now know that not to be true, that the materials from the spill are still working their way through the system. In the fall of 2020, NMED conducted an investigation of heavy metal sediment concentration in the floodplain in the upper Animas, just upstream of Silverton, and resulted in a number of very high concentrated lead areas that were in the floodplain. So these are a concern because during high flow events, spring runoff, these sediments are gradually going to be lifted and transported downstream. There are areas that were former tailing piles that are in the floodplain, and those areas had the highest concentrations, getting into percentages of lead concentration as high as 4.6%. So the results of NMED's investigation into these lead contamination in sediments was validated by an EPA sediment monitoring that was conducted for the Bonita Peak Mining District Terrestrial Baseline Ecological Risk Assessment, which is in draft form and it's currently available. And like our results, the ecological risk assessment results do show high lead values that are in the floodplain of the Animas River and the Bonita Peak Mining District. And throughout their environmental units that they tested, the Animas River definitely had by far the highest floodplain lead concentrations. And those are represented by the yellow boxes in the box plots of the chart. So another potential source of lead that happened prior to the spring runoff of 2019 was the 2018 416 fire that was just north of Durango. The fire burned for 60 days in 2018, and despite an increase in dissolved lead and total lead in spring runoff following the fire, the actual contribution from this event is probably difficult to quantify. For example, the 2002 Missionary Ridge fire, which burned just on the other side of the Animas River and was about 1.5 times the size of the 416 fire, did not result in any detectable lead concentration increase in following years in 2002, 2003, or 2004. But the Mountain Studies Institute completed a sampling and report on runoff metals concentration and did find very high total lead and a dissolved lead detection during their monitoring in July of 2018. So another potential source of lead contamination is the former smelter in Durango. This issue was brought forward in a High Country News article, The Dark Secrets of the Animas River, where they did a great investigation on not just the Gold King mine spill, but also other legacy forms of contamination in the Animas River watershed. And in that article, they brought up the smelter and the high levels of uranium, lead, and other contaminants, and said they could only guess at what lurks in the silt of the Animas riverbed. Well, thanks to a Nuclear Regulatory Commission study that was published in 2015, Groundwater Compliance Action Plan, that was a result of the cleanup of the tailings and smelter site. We do know that there are low risk assessments for lead. So even though it's a low risk assessment, when you're talking about an impaired water body, every source is important. So in conclusion, we do see increased dissolved lead concentrations, and they are sufficient to produce a listing of the Animas River from Estes Arroyo to the southern Ute boundary as impaired for aquatic life use. The Animas River dissolved lead concentrations in New Mexico are now significantly correlated to Animas River discharge, and these high flow events are likely remobilizing lead-containing sediment. And lastly, our probable sources include predominantly sediment deposits resulting from the Gold King mine spill and legacy floodplain sediment concentration in the Bonita Peak mining district that's being remobilized during high runoff. And then other minor contributions include highly turbid runoff from the Hermosa Creek watershed related to the 416 fire and contaminated groundwater in Durango from the former smelter. And last point I'd like to make is we do know that lead contamination from the Bonita Peak mining district is continuing to affect New Mexico, and the problem has not washed away into Lake Powell. And there are a lot of questions still to be asked and answered, and to address these, continued monitoring of this watershed is essential. So with that, I will take some questions.
Okay, everyone. So if you have any questions for Chris, use the hand raise function.
Okay, thank you.
Okay, thanks, Chris and Mark. Chris, that was very interesting, and I think when you hear my talk later on about some of the reservoirs on the Animas, there could be some other discussion. But given the sake of time here, the next speaker will be introduced, and that is Stacy Timmons. Stacy's going to talk about multi-year groundwater monitoring along the Animas River that has been going on through the New Mexico Bureau of Geology and Mineral Resources. So Stacy is a hydrogeologist and associate director of hydrogeology at NMBGMR, which is the acronym or also known as the State Geologic Survey, which is associated with New Mexico Tech in Socorro. Stacy has more than 15 years of experience in New Mexico working on a variety of water issues. She has a strong technical background in groundwater and surface water interactions, water data collection and management, and the geologic influences on water movement, availability, and quality. Stacy's research team has played a key role in developing the current hydrogeologic understanding of the aquifer system along the Animas River in northern New Mexico. And so, Stacy, you are up whenever you're ready. Go ahead and share your screen.
Okay. Present. Start on the first slide. Here we go. Okay. You guys can hear me okay, I presume, because I can see that Emily's signing. Thank you for doing that. And I really want to say thank you to the organizers for putting this together. It's been many years of coming together and presenting and sharing information, and it's been impressive to me how this was smoothly transitioned into a web-based meeting and set up over multiple days instead of all in one day. I appreciate that. And the persistent reminders have been very helpful. So thank you for getting this together. I don't know if anybody was following the agenda closely, but this slot was supposed to be a presentation by Talon Newton. I'm the pinch hitter today. He's having, he's on sick leave right now, so I am at the last minute asked to jump in and give this presentation. So it's not going to be the technical presentation that Talon would have given. I'm just going to give you some background on the work that our group has been doing here along the Animas River. So I just want to start by acknowledging the work that we've been doing here is largely funded by the Environment Department, the New Mexico Environment Department, through EPA sources. Slide changing button. Okay, so just for a little background, we've been working up in this area along the Animas since the 2015 Gold King Mine event happened. There were a lot of questions when that happened about how exactly the groundwater and surface water interact along the Animas stretch, particularly in New Mexico, and how might we see impacts to groundwater as a result of the Gold King Mine. So you can see the map here on the right-hand side, the Gold King Mine way up here in Colorado, and the section of the river that we're looking at primarily here along the Animas from the Colorado border down to Farmington. And so some of the big questions at that time were, you know, is this river really entirely a gaining river, or are there times of the year or sections of the river where we see switches from gaining to losing, and meaning that a gaining river is primarily fed by the groundwater, and the groundwater enters and supports the flow of the river, and losing being the time when, or sections where the river water would sink into the groundwater and influence perhaps water quality. And so we started back in 2015, and I'll go through some of the work that we've done, both to look at groundwater, surface water interactions, and the groundwater quality. So as I said, the research here is largely being led by Talon Newton, and he is here in this image. This was on one of the previous WRI field conferences, having lunch here actually in the Animas River. Alongside of him is Ethan Mamer, who's also worked on this project since the beginning. The field team also includes Scott Christensen here measuring a well, Kitty Picorni helping with data management, and Trevor Clute also collecting a lot of the field data. We've collaborated over the years with a lot of the different groups presenting at this conference, the Environment Department, the USGS, New Mexico Water Science Center, and several others along the way to get this research underway. So I just wanted to real quickly point out some of the just number of data points collected along this river. It's pretty impressive to be able to think back to the level of understanding that we were at in 2015, and the number of new data features we're able to contribute and inform decisions along this river. So in 2015, we inventoried a large number of wells along the river. From that, we were able to measure groundwater levels over the years. And then each year in 2016 and 17, we did twice a year water sampling. And then in 2018, some more detailed follow-up sampling came along. So it's just a lot of data collected to support the science in this region. The folks have been out there in all sorts of elements and conditions. We aimed to give a breadth of understanding so that we can understand how groundwater quality is impacted during low flow times of the year as well as high flow times of the year. And so here we are in the winter collecting water samples. If anybody has collected water samples in the winter, it can be brutal and cold. So Scott's here and Ethan out here measuring groundwater levels in the winter. This is what the actual river looked like, the Animas, with large chunks of ice floating along. And then this little instrument down here is one of our pressure transducers. We have a number of them equipped in wells along the river. Several of them, like this, are actually measuring the groundwater level in addition to temperature and the conductivity of the water. So we can see if there's water quality fluctuations during the time when we're not actually out there sampling. And then we were also able to collect in the spring and summer months So here we are measuring wells. A lot of them are located in these little kind of structures. So in and out of all sorts of interesting buildings. Collecting water samples from people's domestic wells requires a lot of careful engineering to get a good sample and get representative field parameters using our little flow cell here. And then also out collecting samples along the river to compare to the water that we're looking at in the groundwater system, as well as in irrigation ditches. So a lot of this information has been presented in reports and data summaries. If you go to this short link, it'll take you straight to the website on our Bureau of Geology webpage that has reports and fact sheets. And then there's also quite a bit of information available on the WRI's conference webpage for this, this multi-year conference. I'll put that link up again at the end for anyone who needs it. So presently, we are actually just finishing up a couple-year project with the Environment Department. And the goals here in this go-around are to really test out some of the previous work and test out our hydrogeologic conceptual model and try to refine that a little bit more. We're also trying to evaluate the recharge process to the groundwater as we're thinking about water quality impacts. We're also working on a number of the findings from previous years showed certain dissolved constituents in the water having some interesting trends, and so we're trying to discover the source of those along the river in the groundwater. And then finally, some of those constituents that are especially high are manganese and iron in the water. So trying to get a little bit more information about what that is being sourced from. So I wanted to just pause on this slide for a moment and kind of set the stage here. The Animas River, we've probably seen this image over the years or in other presentations. This is just kind of a cartoon to show the different inputs and impacts to the water quality here in the Animas. And so here is the alluvial valley along the Animas River. So it's kind of a sediment-filled, narrow strip aquifer, alluvial aquifer that's inset within bedrock formations that are surrounding it, that build up the mesas and cliffs around the river. And so the river flows down from Colorado and is distributed in multiple diversions in irrigation works, as well as into reservoirs for drinking water. Through the distribution of irrigation, it's basically working as a sort of almost like a recycling effect where you distribute water on irrigated fields and then infiltrates and gets back into the river. So it's kind of this circular process of recharge that's happening along the river. So that's one main mechanism of recharge. And another mechanism of recharge is that there is, flow from the bedrock surrounding the valley into the alluvial aquifer. So those are some of the different considerations when we're thinking about water quality. And I want to also just point out that there's wells throughout this valley that people are using for irrigation, and a few people using it for drinking water. But primarily through this valley, the drinking water sources are public supply centers and community water supplies, and a few people are using wells, private domestic wells for drinking water. So we were able to access a lot of the private wells in the valley to inform the research that we're doing here. I just want to also point out on this slide two other things. One is that the groundwater flow direction is basically flowing along roughly in the direction of the river, so heading in the southwest direction through this alluvial aquifer. And then groundwater is basically flowing downhill into the valley. So, and then the other thing to point out is this cross section here at the bottom. you can see just a very general conceptual here of the geology going from Durango down toward Farmington. And the important thing to notice here is that we're on the edge of a basin. And so the bedrock here, particularly like the Nacimiento Formation and the San Jose Formation, are outcrop in Colorado and go in the subsurface and then come back up as we get closer to Aztec and Farmington. And so those bedrock formations are contributing groundwater as it's flowing through the formation and then upwelling and adding certain constituents along the river valley in kind of the section of the river that I'll get into here shortly. So as I mentioned early on, we were trying to discover where there are sections of the river that are gaining or losing, and some of our work has highlighted that there are times of the year and sections of the river where the groundwater is no longer contributing much water to the river. So the river is neither gaining nor losing. It's relatively flat gradient. And so those areas are up here around Cedar Hill, just south of the dot on the map known as Inca, and then a little bit around Aztec. And so these are some areas that we wanted to really pay close attention to see if there are periods where the river is losing in those areas or if they're impacting water quality. So in the first couple of years of sampling, we repeatedly sampled several of the same sites to see if there were seasonal fluctuations. And so this is a map coverage of approximately where those samples were collected. And then in 2018 and 19, we nearly doubled the number of sites sampled and really, again, tried to focus in on some of these areas where we were concerned about potential losing effects if the river is contributing to the groundwater. And I think Talon would be able to get into a lot more detail about specific geochemistry results, but I think that this slide is a good kind of summary, general summary of the chemistry results, which is that many of the sites have some water quality concerns when we compare them to EPA's maximum contaminant levels. The fact of the matter is that private domestic wells and irrigation wells are really not regulated under these guidelines. So we're just using these as a comparison. But for these locations that you can see here on the map, some of the areas with red have higher levels of total dissolved solids. There's some locations where we see elevated manganese, a lot of areas where we see elevated sulfate, iron, and a few places where we see elevated aluminum. And the fact of the matter is that these, while some of them did show up in the Gold King mine spill, we can't exactly, it's not possible to say that that is the source of these because there's so many other regional sources of these constituents. And so we are suspecting that, and I think that the research is now confirmed that a lot of these constituents that we're seeing are actually contributed from the regional surrounding aquifer, bedrock aquifer, and the upwelling from that feature. Let's see. I wanted to point out that we also sampled, there's these two wells here circled in orange. Those are wells that were completed in the bedrock. So we were able to use those as end member comparisons to the water that we sampled in the valley. And that was really insightful to be able to trace back some of those metal constituents. So we can say safely that these bedrock rock aquifers are contributing some of the constituents that we're seeing elevated in the river valley. And then the last bullet point on here that I wanted just to mention is that a lot of the conditions that we're seeing basically in the shallow surface waters along the river and along the irrigated valleys due to the redox and pH conditions, a lot of the metals of concern from the Gold King mine are basically precipitated out of the water and bound up in clays and other kind of solid forms and not able to make it into the groundwater. So we're not seeing the transfer of some of those metals that Chris was talking about into the groundwater because of those geochemical conditions causing them to precipitate out or bind up on clays. So we have a report that will be coming out in the fall this year. It's in review right now. It will be discussing some of the results of that broader sampling campaign, specifically looking at some isotopic analyses, looking at dissolved inorganic carbon and some of the components of that. We have continued the groundwater level monitoring on a more distributed basis so that we're able to compare the very interesting findings of the 2018 low water year. And then I think that the research further evaluates some of the down gradient changes that we see. So as you go further downriver, we see increases in total dissolved solids and sulfate. And so this kind of helps answer some of the whys about where we're seeing that. So I'll just close with this. If you guys have really hard questions, I'm going to point you to Talon to answer when he gets back from sick leave. His email address is here on this slide if you wanted to take note of that. And then again, that website link and where to go for more information on this project is on our website at geoinfo.nmt.edu. You can search for it through there. That's all I have for presentation now. If you guys have some not hard questions, I'd be happy to try to answer them.
All right, thank you so much, Stacy. Are there any questions amongst our attendees? You can use the hand raise function again if you want to ask something. I'd like to say thank you once again to Melissa, Andy, Anthony, and Brandon for their help in putting that video together. You may remember seeing Alyssa and Anthony present yesterday's webinar session. And if you stick around tomorrow, you'll get to hear a presentation by Brandon Francis on the continued impacts of the Gold King mine spill on Navajo farmers. With that, I'd like to get into our afternoon session today, and we'll be starting with a familiar face by now. So Johanna, I'm sure we're all familiar with you at this point, so I'm gonna allow you to get into your presentation.
Okay, thanks, Mark. I figured I would spare you guys hearing my bio yet again. Let's see here. Let me get my screen shared. And the slideshow going. Okay. Thanks, everybody. Yeah, it's sort of fortuitous that Mark asked me to be the MC today on the day that I'm also going to be presenting some work that we've been doing. And again, the information presented today is just really, really fascinating. And I would say to both Chris and Stacy, there's a number of things that I think we should chat about in what we found in some of this reservoir work. And so I'll talk to you offline. But today I'm going to talk to you about work that I've been doing with my colleagues Jeb Brown and Christina Ferguson at the USGS, New Mexico Water Science Center, as well as some other folks there. And we've also collaborated quite a bit with Dr. Becky Bixby at the UNM Department of Biology. Like Stacy mentioned, we have collaborated with the Bureau of Geology. We've worked with NMED. And I definitely want to point out our funding sources for this work has been the New Mexico Environment Department and EPA. And we've also had really great collaboration with folks from the city of Farmington and the city of Aztec. And so I don't think anyone's surprised at the fact that I'm showing this picture of the Gold King mine spill from August 2015. This was really, this event was really the catalyst, I think, for this work and a lot of the work that we've been doing through everyone on these talks, is really realizing that we didn't have a lot of information about chemistry and biology and agriculture within the Animas and San Juan watersheds. And now realizing that this is an area that's susceptible to some issues, that we really need to dive into things. And so because of that, I'm just going to run through a little overview of mining in the Animas River watershed. A number of people have touched on some of this already, so I won't go into great detail, but essentially the Animas River watershed, especially in the headwater area, has been mineralized both with heavy metals like gold and copper, and also with uranium ore-bearing formations such as the Morrison. And those are pointed out by the yellow triangles, or excuse me, diamonds within the figure on the right there. And then the Gold King mine itself was in operation from the late 1800s to the early 1900s. And during that time period, not only the Gold King mine, but other mines in the area, tailings were just discharged directly into the streams. And it's estimated that 4.3 million tons have been dumped into the Animas River. And so as Chris showed, water is moving these sediments downstream. And so we really need to be aware of what's happening with that. Also pointed out before was the Durango Mill, which is operated as a lead smelter and then also processed ore for vanadium and uranium. Two events in the 1970s also released some waste into the Animas River. The tailings dam at the Sunnyside Mill, which is also located in the headwater area very close to the Gold King mine, as well as Lake Emma, which was a lake that was above much of the mill work area. That collapsed and actually fell into the mine and flowed into the Animas River. And then finally, again, in 2015, the Gold King mine release occurred. And so from this, getting to talking with especially Dennis McQuillan and others and saying, well, we've got a couple of reservoirs along the Animas River that are located in New Mexico that are also used for drinking water. And those are pointed out at the bottom of the figure. They're the Aztec Reservoir number 1 and the Farmington Lake. These are both man-made, and we're really interested in seeing what, if anything, the sediments can tell us. And so the main objective of this work was to evaluate the sediments deposited in these two different drinking water reservoirs to ultimately understand the history of water quality and the mining legacy captured from a highly mineralized watershed. Now again, this watershed has had a lot of mining. This is a geologic map that Christina put together and really shows some of the different geology as you move downstream. And ultimately, once you get into New Mexico, as many of us know, it's a lot of sandstone and shale and sediment. But further upstream, you have more crystallized deposits which contain these heavy metals. To go into a little bit of detail about the two reservoirs specifically, on the right side of this image is the location of the Aztec Drinking Water Reservoir number 1. It's a pretty small reservoir. It was built in 1947, and then it was drained of water in the fall of 2017. And the reason for that is because ultimately the sediment in this reservoir was dredged and deposited in a landfill. So the sediments were actually mostly dry when we did sampling, and so we did have to dig trenches in the sediment in order to sample. And I have some pictures of that. To the left on this image is Farmington Lake. And so you can see these two reservoirs aren't that far from each other. Farmington Lake is much larger. It's younger. It was built around 1960, and it was completely full of water when we did the sampling. To look at these from an aerial view, to just get a little bit more acquainted with these two reservoirs, this is the Aztec Reservoir. And I want to point out a couple of things. So in the image on the right, we have 4 aerial photos labeled A, B, C, and D. And the first one, labeled A, is from August 2005. And there's a few things I want to point out here. The first of which is on the right-hand side of that image, it says irrigation input. That is one of the inputs and the original input actually to the Aztec Reservoir that comes through a ditch, an irrigation ditch, that actually starts up near Cedar Hill. On the far left-hand side, kind of up to the top and left, is the Animas River input to this reservoir. And that has a pump that pulls water directly from the Animas River into the reservoir. And depending on the time of year and what's happening, the operators of the reservoir will change what the input is from. The other thing to look at is the location of the outlet tower. So that's just above where it says number 4 on this image. It might be a little bit hard to see, but that is where water is actually pulled from the reservoir and put into the water treatment plant that's just off the screen there at the top. And then from there becomes drinking water. On here, we also have the locations of the 4 trenches that were dug, and they're labeled 1, 2, 3, and 4, kind of in a semicircle there. The final thing to point out on this particular image is the fact that you don't really see any other structures. You basically just see water in this image. Then if you go over to March 2007, you now see some black lines in the image. And these black lines are actually called baffles. And the baffles are there to separate out the water from each of these different compartments and to help with sediment deposition into the reservoir. So basically this reservoir and many of the reservoirs in the Southwest, the first step is to remove the sediment from these reservoirs. And so you can see basically on the kind of left side of the baffles where the Animas River input and the irrigation input are, is that the coloring of the water is a little bit different from the areas with 2, 3, and 4. If you go down to the C image on the left-hand side there, you see that that's from June 2011. And now what you don't see is the baffle that goes from the Animas River input down. That baffle at that point had been covered in sediment and collapsed. And you can tell that also by the different coloration there. And then finally, by in the next slide, you can, sorry, I have people's faces on that side, so I can see Emily and Emily, so I couldn't see the date there. So in November 2013, you can now see that not only the one baffle by the Animas River is gone, but also the one by the irrigation input. And so that could potentially affect the sedimentation in these reservoirs. And then the final image on here to point out is the conceptual model at the bottom that just shows where the trenches are, kind of in cross section compared to the irrigation input and the Animas input. And you can see that trenches 1 and 4 are actually a bit thicker in sediment than trenches 2 and 3. And so we ended up using 2 and 3 a lot for consistency with sedimentation. To show you the Farmington Lake aerial view and conceptual model, this is set up in a very similar way to the last one. And so basically on the left-hand side is the Animas River via a pump. The right-hand side is the Animas River ditch that comes in. Something to point out here in the first image is in 2005, the water from the ditch was basically just going directly into the river. By 2015, in the next figure over, there's a kind of a serpentine S-looking structure there by the ditch, and that is a structure put in to help to drop out some of the sediment. So it's sort of a first attempt at getting some of the sediment out. And then ultimately by 2019, the Animas River input also has a spot where sediment can be released. For the Farmington Lake, we took 4 samples as well. Core 1 was close to where the ditch input is. Core 2 is near the lake input, and then Core 3 is close to the dam, and Core 4 is where we believe the thickest amount of sediment was located. One other thing to point out on this slide is that we were able to do some water quality parameter measurements within the lake. The lake is pretty deep at the deepest point, 90 feet. And we found that there's a slight thermocline where the water temperature changes as you go down with depth. And what that could mean is that this lake has the potential to do what's called a turnover, which could potentially affect how sediments are deposited. Couple of slides on sediment, on the sediment collection, and just some pictures to show what that looks like. This is the collection at Aztec. The images on the right show the first one, actually the top 2 on the right show the layering that we found in the sediments in the Aztec Reservoir. And below is one of our awesome technicians, Tyson Hatch, doing some sampling and learning how to do that. And then, of course, the bottom right is some dried sample. For Farmington Lake, like I said, it was full of water, so we actually had our boat crew out of Austin, Texas, come up with the coring boat, which is shown here. And Craig and our own Jeb Brown there are sampling sediment in a core where you can see the sediment at the bottom of this core and water at the top. And then Jeb is helping with one of our emeritus scientists, Mike Carlson, and looking at that long core. And then the final person to point out here is Chris Braun from Texas, who came up and he's helping me subsample some of those sediments. So what we did then is some of the analyses that we did to try to understand the chemistry of these sediments are to do X-ray fluorescence with a handheld X-ray fluorescence handheld instrument. And on the left-hand side there is Dennis McQuillan helping us and collaborating with us on this particular site. And then that's me on the right-hand side, hiding under my hat. So we also analyzed total chemistry. We did some mobility experiments, which I won't unfortunately have time to talk about today, but I'm happy to talk to anybody otherwise. We did some loss and ignition. We also looked at some sediments under a scanning electron microscope. And we did some age dating by analyzing cesium-137 concentrations on the Aztec sediments. So I'm going to jump right into some of the results. And again, for the sake of time, I won't be able to go through everything, but if people are interested, I'd be happy to talk about it more. The information about the Aztec Reservoir is basically in press with the journal Environmental Earth Sciences. That should be out hopefully by the fall, and I can certainly let people know when that has been published. So in the Aztec Reservoir, this image shows the face of one of the trenches, and the graph on the left-hand side shows the concentration of cesium-137 in millibecquerel per grams, and then the y-axis shows the depth of the sediments. The reason to analyze for cesium-137 is because it's a byproduct of nuclear weapons testing, and the peak of that was around 1963, 1964. And so if you can find in the concentration of your sediments that peak, then you can assign an age to that particular location in your sediments. And because we know that this reservoir was built in 1947, and it was emptied in 2017, we could then have 3 dates that we can assign and actually create a sedimentation rate curve, which can then help us assign rough dates to where the sediments are. We weren't unfortunately able to do that in the Farmington Lake core because the lake is too young. It wasn't built until 1960, and so some of these geochronology techniques that we use, we weren't able to. That being said, we are working with, Jeb is our sediment specialist, and we're working to figure out sedimentation rate based on compaction and grain size in this core, so stay tuned for that. And then this, of course, you can see kind of the difference, the different look of this core. To jump into some of the results as far as the chemistry is concerned, on the left-hand side is the Aztec Reservoir, and on the right is Farmington Lake. The y-axis, again, is the depth of sediment, and then we have each one of the samples shown on the x-axis with weight percent concentration of each of these major elements. The takeaway here is that the concentrations in the sediments are similar within the trenches or cores themselves and also among both of the reservoirs. And this is not surprising because major elements, things that you would find in higher concentrations, these are common in this watershed, and so any sort of variation would probably be some sort of natural variation in the watershed. The only thing to point out is that in core number 1, all the way on the far right of this image, that's a much shorter core. To remind you, that is a core that is located next to the ditch input from of Farmington Lake. And so you do see here that there's some calcium and aluminum variation, and so we're looking into what that might mean. So to be continued on that. To look at some trace element differences, on the left-hand side again is the Aztec Reservoir. Both of these figures show arsenic, uranium, vanadium, and copper across the x-axis, and then the depth of the sediment on the y. An interesting thing to point out here is the concentrations of arsenic, uranium, vanadium, and copper in the Aztec Reservoir. You can see where we have chemistry of the bentonite layer, which is a clay layer that is often used as sort of a confining layer in reservoirs because it swells up and can create a pretty good seal. But those concentrations are quite low in these elements, but then you get into kind of the 1947 to 1965 or so range, and you actually have some relatively high concentrations found in these sediments. And what we find pretty interesting is that, especially with the uranium and vanadium, with that mill being located in Durango, that could potentially suggest that those concentrations in the reservoir are related to that mine or excuse me, that mill or some of the larger mining legacy. The arsenic is known to be co-occurring with uranium vanadium minerals. It could also be coming down from the Silverton area. And then the copper, I'll show you an image here in a minute of copper, of a copper sulfide we found under the SEM. And so that we do feel like is likely a grain or multiple grains that have traveled down from the Silverton area. The Farmington Lake, these results are pretty new actually, so you're getting a first shot of some of these results. And so you can see in Farmington Lake that the patterns are very different. The depth of cores are very different, so we're still working out how we want to evaluate that, but you do see some variation. I added in, just after Chris's talk this morning, I added in some slides on lead. I realize that these don't have the exact same elements. That's because I hadn't worked this up to present today, but I thought, oh, maybe people would be interested in seeing these lead concentrations. And so in the Aztec Reservoir, lead right around 50 or 60 centimeters below the surface does have a spike, at least in one of the trenches. And so we do talk about that a little bit in that paper. And then you can see in Farmington Lake that we've got quite a bit of wiggling going on with lead. Also want to point out before I move on that in regards to what Stacy was talking about with the groundwater, with iron and manganese, we did find some interesting variation within the cores of Farmington Lake in regards to manganese. And so we're looking into that and definitely want to talk with Stacy and Talon about what that could mean. As far as how high of concentrations there are in the sediments and what that could potentially mean for any sort of toxicity, this slide represents what's called the toxicity characteristic leaching procedure. I know that's a mouthful. We abbreviate that to call it TCLIP, TCLP, and the TCLIP rule of 20 is that if your concentrations in your total sediment are less than 20 times the TCLIP amount, then it's considered okay for those sediments to be put into a landfill, that they won't be leaching high concentrations of potentially dangerous elements. And so the takeaway here is that all of the 8 elements, the 8 RCRA metals that are of concern are below those values. We didn't, we didn't measure mercury in Farmington Lake on these, but we will be doing that on some of the mobility experiments I mentioned. I'm just about done. I know I went over a little bit. The Aztec Reservoir, we did some scanning electron microscopy. This is a result of one of those. I just want to point out that the spot that says number 4, that's where we found what we think is chalcopyrite, which is a copper iron sulfide. And that is certainly found up in the Silverton area. Lots of clays in this slide as well. And then number 3 is actually a gypsum grain. So that's a calcium sulfide, which could also contribute to some of the chemistry. We plan to do this the same thing with Farmington Lake. We're just kind of waiting for labs to open up due to this pandemic. And then the last results slide here is about diatoms. And so this is work that Jeb and our colleague Becky Bixby at UNM have worked on, where diatoms, if you're not familiar with them, are single-celled alga with a cell wall of silica. They're pretty cool little creatures. And looking into this, we found that diatoms can potentially be an indicator of poor water quality. And what we found is that there wasn't any indicators of poor water quality. So that means that the reservoir maybe hasn't been bombarded with really high metals over the years. Both of these reservoirs do turn off inputs, as was mentioned earlier, if there's high turbidity or certainly when the Gold King mine spill came through. In the Aztec Reservoir, the prominent species were found to be benthic, which are the species that are going to be kind of along the bottom of the reservoir and within the sediments. And Farmington Lake, the prominent species are both planktonic and benthic. So you've got these guys on the bottom of the reservoir and also kind of floating around there. And so I'm sure Jeb and Becky would be happy to talk about that more if people have questions. So just to wrap it up, the kind of major takeaways here are that there's evidence suggesting that mining activity is recorded in the sediments of the Aztec Reservoir. We're still looking into what this could mean in the Farmington Lake. There's definite changes in trace element chemistry seen in both reservoirs. Those concentrations of arsenic, uranium, vanadium, and copper at the base of the Aztec Reservoir are very interesting and make a definite change as you go up in time. The major elements are variable due to weathering of natural sources within the watershed, and overall the metal concentrations do not exceed the RCRA limits for landfill waste. So, and again, I barely scratched the surface on the information that we have, and so I'd be happy to take maybe 1 or 2 questions here. I know we're running low on time, but my email address is there, and feel free to reach out, and we'd be happy to talk to you about it.
Okay, thank you so much, Johanna. Do we have any attendees who would like to ask Johanna some questions? You can use the hand raise function again, or as well our Q&A boxes.
Introduce our next presenter. Keeping with the the family here, we've got another Another person from USGS, one of our relatively new hydrologists, Erin Gray, is going to be presenting on some work that we're looking into at the Lee Acres landfill, which is near Farmington, New Mexico. I realize this doesn't really have much to do with the Gold King mine, but figuring that we're working towards looking at the broader understanding of the San Juan and Animas watersheds, and also with this source tracking project that we're going to be doing, we thought that this would be a really good venue for Erin to present some of this information. And so, like I said, Erin is a hydrologist at the USGS and the New Mexico Water Science Center with myself and Jeb and Christina. There she applies her background in geochemistry and mapping to various projects related to water resources, source water investigations, and environmental contamination. Prior to joining the New Mexico Water Science Center, she worked for the municipal water provider in Tucson, Arizona, where she learned about water resources management and planning while supporting large-scale recharge operations. So take it away, Erin.
Great. Thank you for that introduction, Johanna. I'll go ahead and share my screen. All right. And I'll also point out I'm presenting from the field this week. I'm in my truck at a motel, and so I apologize in advance if there are any road noises or connectivity issues. I think this is my best shot at having a good Wi-Fi the whole time. But yeah, my name is Erin, and I'll be talking about our work at the New Mexico Water Science Center with the BLM at the Lee Acres landfill. My co-author on this presentation and my co-chief on this project is Christina Ferguson, and I'd also like to thank the help that we've had at the center from Johanna, Kim Beisner, and Fred and Eric, who have really been the project managers for this project for years. So I'll be talking a little bit about the monitoring that we do at the Lee Acres landfill, but also talking about a new study which is investigating the source and mobility of manganese in groundwater and sediments at that site. So the Lee Acres landfill is located in the community of Lee Acres. It's about 6 miles east of Farmington. The landfill itself is adjacent to an arroyo that directly drains to the San Juan River about a mile southwest of the site. And the landfill contained a number of liquid waste lagoons that stored a number of wastes, including chlorinated solvents, spent acids, and produced water from oil and gas fields, among other wastes. And that's all on about a half a square mile surface area. Despite that sort of small footprint, the landfill is estimated to contain about 800,000 cubic yards of waste and contaminated soils. So zooming in on the landfill a little here, you can see the outline of the landfill in red. It's directly north of a former refinery. Both sites, both of these sites actually had liquid waste lagoons at the surface. You can see that arroyo adjacent to the landfill, draining to the San Juan, right next to the Lee Acres community there. And the landfill is on BLM land. So the BLM land leased the land and to the county, to San Juan County, from 1962 to 1986, where it was operated as a county landfill in that time. In 1985, there were actually investigations going on at the landfill related to investigations by NMED related to chlorinated solvents that had been found in some of the lagoons. In 1985, around that time, there was site workers on site when heavy rains caused a breach in one of the liquid waste lagoons, causing waste to spill into the arroyo, and also causing some health issues among site workers and witnesses there, who reported feeling dizziness, trouble breathing, skin rashes, and also an H2S gas smell. So due to that incident in 1985 and continued investigations of chlorinated solvents and heavy metal contamination at the site, the landfill, was shut down in 1986 and was placed on the national priorities list by the EPA in 1990. So since that time, the USGS has been involved. The BLM is the manager of the site, but USGS has cooperated with the BLM to produce multiple studies and to do a lot of the monitoring at the site. So notably, a hydrogeologic characterization was published by the USGS in 1987, and we began regular groundwater monitoring at the site in 1983. After that, in 2004, the EPA published its Record of Decision, or ROD, for the site, which outlined 4 selected remedies to deal with, the VOC and heavy metal contamination. The first selected remedy being a landfill cap installation, so a capillary barrier to cover the liquid waste lagoons. Surface runoff controls, those are related to the installation of this county highway that goes through the site. And also institutional controls, so the site was fenced off and the public prohibited from accessing the site, preventing potential exposure. And the final selected remedy is monitored natural attenuation. So on this map on the right, you can see again the footprint of the landfill itself, and you can also see 8 monitoring wells that are still being used to monitor for regular monitoring at the site. And I do want to point out, these are not an exhausted list of the wells that exist at the site. There's been years and decades rather of investigations. There have been other boreholes, there have been other monitoring wells that have been monitored over time. But these sort of 8 wells that you can see on this map are the 8 that are used currently for the monitored natural attenuation. So they're the ones being used for the regulatory monitoring that's performed at the site moving forward. And so those are the ones that we'll be focusing on in this presentation. And in particular, I just wanted to point out BLM 39, which is this northernmost site. We'll be talking about that well a lot. But yeah, it's this BLM 39 is this well that's up gradient slightly of the landfill in the Arroyo. So before diving in too much further into the regulatory process or the monitoring that's been going on at the site, I wanted to touch on the geologic setting where the landfill is. It's within the San Juan Structural Basin, and as I mentioned, it's directly adjacent to that to an arroyo. Quaternary alluvium in the arroyo is about 20 to 60 feet thick in that area. And underlying that alluvium and on the sides of the alluvium, you see Nacimiento Formation. So that's a mudstone sandstone formation. The mudstones contain swelling clays, and sandstones are medium to very coarse-grained Arcosic sandstones. And underlying that, some of the lower layers of this formation contain carbonaceous mudstones. So I mentioned some of the selected remedies, one being landfill cap installation, and that cap was really installed to slow infiltration through the lagoon, the former lagoon ponds. You can see on the right side of this slide the sort of evolution of that cap installation, 1997 pre-cap installation. In 2005 is when it was installed, and you can see the cap is in place as well as the county road. And in 2020, you can see that it's got vegetative cover over the landfill cap. And this gets monitored regularly. It gets monitored, there's some lysimeters that are monitored, and also the vegetative cover is monitored regularly. And that monitoring shows that the landfill cap is operating as expected. Nevertheless, manganese is still a contaminant of concern at the site. So I mentioned earlier, BLM 39 is one of the wells that is still on the regular monitoring plan, and it was selected by the EPA's Record of Decision to be sort of the background well, so the well that that is meant to show natural changes in the background manganese concentration at the site. Also, the EPA's already set sort of an average background target for monitored natural attenuation at 346 parts per billion of manganese. And you can see on this plot, manganese over time is fluctuating around that background manganese concentration, sort of as you would expect. It seems to be, you know, average value of 346 parts per billion. So let's look now at some of the other water quality data at the site. So on the right, we see, again, the landfill is outlined in red, and the 8 monitoring wells are shown there. And the way we'll actually look at this data, we'll layer on the manganese data, manganese over time at the site, starting with the background well, BLM 39, moving down, and then actually bracketing this area of higher concentration, which is BLM 77, 80, and 62. These 3 wells that show some higher concentrations of manganese. So we'll sort of work from lower concentrations up to higher concentrations of manganese. So here's BLM 39 of this data we already looked at. It moves around this background average level set by the ROD, moving down at BLM 45. You know, concentrations of manganese are consistently, you know, within the range of background. Same at BLM 60 and BLM 68 and BLM 75. Now we'll layer on BLM 80, which is in this cluster of wells that has higher concentrations. Actually, it still seems like its background is similar to what we see at BLM 39. Layering on BLM 77. Now we can see real spikes in manganese concentration at the site. One in 2004 and one in 2013. At BLM 62, we also see a spike in 2013 that corresponds maybe with the spike at BLM 77. However, there's a spike in manganese concentrations in 2007 that doesn't seem to appear in other wells at the site. So that's interesting to us. This BLM 77, 62, and 80 are really close to one another. They're very proximal to one another, but they show very different behavior in terms of their high manganese concentration events. So this plot is great at showing the spikiness, the really high manganese events. We'll also look now sort of at lower concentrations of manganese and how their baseline manganese might be different. So to do that, we're basically looking at the same plot, but manganese will be on a log axis here. And we're just going to look at BLM 39 and then those cluster wells. Here's BLM 39, our background well, BLM 80, and BLM 77, which interestingly seems to have sort of a lower baseline manganese concentration than BLM 80, which is very close to, or even BLM 39, the background well. BLM 62, maybe prior to this 2005, also has maybe a similar baseline manganese concentration as BLM 77, but we see that after it spikes in 2007, it never returns to those levels, and not after 2013 as well. So that's interesting. There's 2 things here, right? There's spikes in manganese concentration. You know, we have the high manganese concentration events, and also differences between sort of baseline manganese concentrations at these sites, which we find interesting, particularly at these 3 wells that are clustered so near each other, have such different sort of manganese behaviors. So that's something we'd like to investigate and understand what's driving those differences. Here we have, this is a cross-section created in the 1987 report, and you can see on the east side of the cross-section is really close to those cluster of wells. So one thing we'll think about when we're trying to think about differences, what's driving differences in the behavior at these wells, is well depth. So on the map on the right, you can now see the depths of the wells below top of casing to the bottom of the screen for these wells. These wells are all screened to 10 feet. The screens are all 10 feet in depth on these wells, and they were all drilled to straddle the water table. So that's one question we have. Maybe the differences in depths at these wells, maybe the water table is changing over time, driving some differences in behavior. Maybe they're actually tapping into different formations. The cross section here would show that they're all screened within the Nacimiento formation, but that's something we also want to investigate. Could there be, you know, lenses of different material in these areas that are driving differences, the differences that we see in the manganese data? One final thing I'll point out too is that these wells were cased differently. So BLM 80 which again has sort of consistently lower manganese concentrations really within what we would expect from background. BLM 80 is the deepest well here, and it was cased with PVC. Its case and screen are both PVC. BLM 77 and 62 are both stainless steel cases, and Fred Gebhardt, who's done a lot of the monitoring at the site, from his knowledge of the area, the water quality in the area, believes that that could be another driver maybe in some differences in water quality from the wells. So we've talked a lot about background sort of manganese concentrations. Now let's talk about what could be mobilizing manganese in the sediments at the site. So on the right, you can see some manganese oxide minerals. So these could exist in the sediments. They could also form in the sediments under the site. And on the left side of the slide, you'll see the redox ladder. So we believe that redox might be driving some changes, or that's one hypothesis of what could be happening. Redox could be driving some mobilization of manganese from the sediments into groundwater at the site. You can see that manganese oxides reduce they're sort of third down on the ladder below oxygen reduction and below nitrate reduction. Once nitrate is reduced, you would expect maybe manganese oxides to be reducible. So we'll look at some of the historical data from the site to understand if this could be a factor. So here we're going to look at a cross plot with nitrate on the y-axis and manganese concentrations on the x-axis in log scale. And what we would expect is, as I mentioned, as nitrate concentrations, as nitrate is reduced, as those concentrations go down in groundwater, we would maybe expect to see increases in manganese if reduction were responsible for some of the manganese mobilization. So again, we'll layer on our well data, starting with background, and some of these wells that we never really see high concentrations of manganese. And now we're at our cluster of wells, our high concentration wells, starting with BLM 80. We can see it never really exceeds background concentrations of manganese. At BLM 77, we do see what's a trend. The highest concentrations of manganese are correspond with samples that had low levels of nitrate. And finally, BLM 62 never has high concentrations of nitrate, but the redox conditions at this well is something that deserves more investigation and something that needs more data too, including dissolved oxygen and DOC. So that'll be part of our sampling plan moving forward, which we'll discuss in a bit. So far we've talked about a few different things. We've talked about background manganese in sediments at the site. We've also talked about manganese mobilization. So we'll try to align those concepts into a conceptual model for the site that should help us build our sampling plan for how we're going to answer some of these questions about what's causing high concentrations of manganese. So our conceptual model will be aligned on two axes, the first being related to manganese availability in the subsurface. And the positive extreme of this axis is that manganese is ubiquitous in the subsurface. So it's sort of available for mobilization into groundwater everywhere in the sediments. On the other extreme, we have that manganese does not really exist in the subsurface above background levels, and that any spikes in manganese concentration are the result of leaching. On our other axis, we have more like the environmental conditions that would mobilize manganese into groundwater. So on the negative extreme, we have conditions that would mobilize manganese into groundwater are not really prevalent in the subsurface anywhere. On the other extreme, those conditions are ubiquitous everywhere in the subsurface. So, and it makes sense. We're probably not in any one of these extremes, right? We're probably not in any far corner of this plot, but the ground truth is probably somewhere in between. And hopefully our sampling plan will sort of guide us to where we are. And even some of the historical data we have, which, we have a wealth of data, can help suggest us towards directions where we might be or where we might not be. So let's talk about that now, how our sampling plan will sort of address these two axes and hopefully place us within this conceptual model somewhere. So first, sort of dealing with the availability of manganese in the background, we'd like to drill some more boreholes and install some additional monitoring wells. So the first location we're really interested in is up gradient of BLM 39, that background well. So maybe drilling a core there so that we can do some sediment analysis and better understand the concentrations or the amount of manganese that is in the sediments there, sort of reinforcing or building on our ideas of what background manganese is at the site. We'd also like a borehole near that cluster of wells. This would help with several things, understanding, manganese that's in the sediments, and also understanding differences between the alluvium and the Nacimiento formation there, and also understanding where exactly that contact is, or if there's, other lenses or something that could be explaining some of the differences in the manganese concentrations at those wells. We're also interested in a borehole near former refinery waste ponds, which you can see here outlined in yellow. So that will help us get sort of constrain our ideas about manganese in the background, manganese in the subsurface. We're also going to try to, we're going to increase our sampling analytes to include an expanded suite of metals, dissolved oxygen, sulfide, and dissolved organic carbon. So these analytes should really help us better understand the redox chemistry at the wells. So that's really driving at the mobility of manganese in the subsurface. And then the final part of our sampling plan is sediment sampling and a sediment experiment. So that kind of marries these two ideas of the sediment that's in the background, that's in the sediments, and then introducing experiments that would help us better understand what mobilizes those sediments. And we're still not totally clear on what direction we'll take there. We might do some kind of a batch mobility experiment or a sequential extraction. So that's still sort of being discussed and reviewed, and moving forward, we'll hope to have more information on that. So our timeline for the project, right now we're doing background investigation and site reconnaissance, and then the manganese study will officially start at the beginning of our next 5-year agreement with the BLM in July 2021. So shortly after that starts, we'll begin drilling July 21 and performing the sediment experiments. From really starting that year through 2023, we'll be increasing the annual regulatory sampling to semi-annual, and we'll be using that expanded suite of analytes that I mentioned. And finally, you can expect an interpretive report on the manganese study to be completed in early 2024. Great, and I think that's a little over time for me, so I'll take any questions if you have them. And yeah, if you also have questions for me or my co-author, Christina Ferguson, our emails are here as well.
All right, thank you so much, Emily.
This is actually going to be a poster presentation of sorts that Michael Whiting has actually recorded a little presentation just to show everyone. So let me just introduce Michael, and then Mark will play that video, and then we will have the giveaway at the end, and then we'll adjourn. So thanks for everybody for hanging in there with us. So Michael Ray Whiting is a current graduate student at New Mexico State University seeking his master's degree in plant and environmental sciences. Michael was born and raised in Yuma, Arizona, where he enlisted in the U.S. Army upon graduating from Cibola High School in 2009. In 2016, he received an honorable discharge at the rank of sergeant and began his bachelor's degree in geology at NMSU. In 2019, he received his bachelor's degree and started his work in plant and environmental sciences as a graduate student. And Michael's going to present on toxic metal uptake by corn. So this is a really interesting topic as well. So Mark, I think you can go ahead and start the video.
Hello, my name is Michael, and thank you for viewing my poster and listening to this short presentation. In 2018, a graduate student found higher than recommended levels of lead in 3 out of 30 corn kernels in the San Juan Animas River areas, and this study was born from those initial findings. The study was broken into 3 main periods: the pre-growing, growing, and harvest seasons. During the pre-growing season, 5 fields were selected for the experiment through volunteers, 2 fields along the Animas, and 3 fields along the San Juan River. Each field was sectioned into 4 quadrants, and 3 sampling locations were randomly picked within each quadrant. Initial portable X-ray fluorescence, or PXRF, scans were taken at this time, as well as surface soil samples for ICP analysis. The PXRF analyzes total elemental concentration in the surface soil and is well correlated with lead and arsenic in the lab, but not aluminum. During the growing season, leaf tissue samples were collected from the 5 fields using GPS coordinates marked during the pre-growing season. At the same time, plants were flagged with orange marking tape for easier identification in the future. These samples were transported back to New Mexico State University, washed, and dried in an oven at 65 degrees Fahrenheit until fully dried. They were then ground in preparation for microwave digestion. During the harvest season, corn cobs, the husks, and kernels were collected from the same plants previously sampled using GPS and the flagging tape placed in the previous season. Just as with the leaf samples, the corn cobs were transported back to NMSU, where they were processed and prepared for microwave digestion by washing, separating the corn husk from the corn kernels, drying them, and finally grinding them. We are still waiting to get back to the lab after COVID to finish digesting and analyzing all of these samples. After harvest season, we rescanned the fields using PXRF and collected some root samples. The literature shows that most plants will concentrate heavy metals in their root systems. The research team believed this additional data would help us understand how the heavy metals are moving within the soil and plant systems. Thank you again for your time and attention. Please enjoy the rest of the conference.
All right. And Michael is available to take any questions for anybody who might have any. Again, you can use the hand raise function or our chat box to ask your questions. And as you can see in the chat as well, I've inserted a link to where you'll be able to find the PDF version of Michael's poster if you want to refer to it later. But thank you again, Michael, for taking the time to record a short poster presentation. And that brings us to the giveaway prize drawing for today. As Johanna mentioned at the beginning of the session today, we have 2 NMWRRI coffee mugs that we'll be giving away, along with a poster set of the hydrologic cycle that was donated by USGS, another copy of 100 Years of Water Wars in New Mexico, and our grand giveaway prize today, a blue fluorite mineral that was generously provided by the New Mexico Bureau of Geology's Mineral Museum. So we've done our drawings, and so remember, you have to be present during the webinar to qualify for the drawings. And so our winners today include Topher Lewis, or Christopher Lewis. I think I saw him there. We have Terry Austin, both of you each receiving a Anamwiri coffee mug. We also, our poster set today will go to Norman Norville. So congratulations, Norman. The copy of Water Wars will go to Robert Gomez. Congratulations, Robert. And our top prize for today, the blue fluorite mineral, goes to Forrest Vaughn. So congratulations, Forrest. Congratulations to all of our prize winners so far. I'll be reaching out to you for a shipping address to be able to send you all your prizes. And remember, tomorrow we'll be doing our grand prize giveaway, which is a full day float trip on the Animas or San Juan River, provided by Desert River Guides of Farmington, New Mexico. You'll be able to redeem this in spring of 2021 when Desert River Guides resumes their trips on the Animas or San Juan rivers. But stick around for that tomorrow, and stick around as well for our list of presentations that will be taking place tomorrow as well. Lots of presentations focusing on agriculture, as well as oil and gas impacts, opportunities, challenges in the watershed area. So thank you, everyone. Thank you as well to our ASL interpreters, Emily Newberry and Emily Peroni, for their interpretation throughout this webinar series. And I hope to see all of you here again tomorrow. Thank you so much, and have a great rest of your day.